Okay, so today's the day where we plod forward. Any questions before we go on new paths? I sense a readiness for spring break. Me too. All right, so boy, I've got a huge amount of material. I don't know how much I'll get through it. Part of the problem is that I changed up a whole bunch of stuff from last semester and haven't had a chance to test it all. So who knows how today will end up going if we get to that point. We'll find out. Let me start. So one of the issues now that we're moving into P3 is that there's a lot of stuff that some of you may not have had much experience with. So we're going to be dealing with inheritance heavily. I would guess about half to 2/3 of you maybe feel comfortable with inheritance. If I throw in virtual functions and pure virtual functions, then I think that number drops significantly. No fault of your own. I just don't think there are many courses that spend much time dealing with that in any detail. So we'll be looking at that. And exception handling, try, throw, catch, is also used heavily from here on out. So I want to spend part of that time just kind of talking about those concepts. The exception handling stuff I'll roll into when we're talking about the project. But I did want to start with kind of a short in-class activity. And if you go looking at your assignments and projects folder, I've got one in here, in class assignment 5, inheritance or not. And I've got two files in here. And one of them, I believe it's shapes. Let me look at it here. Shapes uses inheritance and virtual functions. And shape shifter uses one class and no inheritance. They both do the same thing though. So what I'd like you to do is, there's nothing here to turn in, is to, if you're willing, get together with someone and look through this stuff. And I need you to come up with an opinion of which of the approaches you prefer and why, and also to just have an understanding of how they're working functionally, because that'll be important for moving forward. And if you do, and to the extent you have questions, I hope you'll be a bit aggressive about asking them. I'm just going to let you take 5 to 10 minutes. There's some diagramming I need to do, and I'm going to do that while y'all are working on this to save time. And when we bring it back together, we'll talk about it and I'll field questions. But to the extent that you're apprehensive about asking a question and having everyone stare at you, I hope you don't have that fear, but I understand if you do. Just remind you that I do have this Piazza in-class Q&A section here, and start pushing your questions in there, and I'll answer them anonymously then in that case. Okay, so 5 to 10 minutes, get together with someone, look through those, understand how they work, figure out what you don't understand, and which you prefer. So I normally do this with an anonymous poll, again, to try and get more answers, but I don't have any polling tool going this semester. So by a show of hands, for those who are not afraid to show their hands, how many people prefer shapeshifter? I see a couple modest hands. Thank you, thank you. All right, we got two. How about who prefers shape? All right. Why do you? So I assume that y'all compiled it and ran it. Why? Who wants to say why they prefer what they prefer? Oh, we're all friends here. No one's not gonna call you out on it. Yeah, go ahead.
I think it's just easier to understand when you read it what's happening and how it's supposed to work.
You're talking about the one that's up here, the polymorphism and inheritance one?
Yeah, it's kind of intuitive what it's trying to do and what you're accomplishing with the inheritance.
Okay, so it seems to be a little bit more intuitive, a little bit more readable. How about shapeshifter? Who wants to go on the record for why they prefer shapeshifter? You want to throw out the reason? Is there a reason why you prefer it? Or, huh?
I don't like it.
You don't like the other one, or you don't like this one?
I like this one.
You don't. Oh, you don't. You don't like shapeshifter. All right.
Enumeration's cool.
Enumeration's cool. All right. I'll go with that.
It's easier to write. Yeah.
Tell me about easier to write.
I need to know about inheritance or virtual functions and all that.
Okay. So yeah. I'll give you that. Certainly, given what you may have been exposed to so far, there's not a lot that is new here that you haven't seen already. Right? I would imagine the most complex thing we have here is what? Enumerations, really. Assuming that you've used dynamic memory and so forth. All right. So the argument I would give for using shapes is that you are pushing as much of the decision making as possible down to the compiler, and that's then taken out of your hands, and you're removing from your responsibility things that these kinds of decisions, right? Determining whether it's a circle or whether it's a triangle. These decisions are, in this case, in the shapeshifter case, being made by you and being evaluated at runtime. So, without getting hung up on too much of the philosophical underpinnings, I would just say that that's probably the greatest argument I could give, is that this one is putting more responsibility on you that you could give to the compiler. And then I'd also then take a look at what is a use case where you have to add another shape. So when we add another shape here, let's say we want to add square. Then I suppose we could still circle, triangle, square. So I guess we could use base and height on that. Well, square we just need one, so I suppose we could add another constructor here. Color, this would be an integer. I guess you just fill in the base. Color, base, it's B, height, it's -1. So we go ahead and use base for two different things here. That's fine. Radius -1, type, square. And where else do we have to make changes here? We have to add another if statement. Square, base times base. Any other changes we have to make? We'd have to change up our menu. How many colors do we have? Where are these colors coming from? Am I just choosing an arbitrary letter for that? All right, Q. And then do a fairly large square. So set color, stats. I guess the rest of that'd be all right. What about this one? So this one we'd have to go ahead and basically create a whole nother class declaration. There'd be a constructor for that. And that would do it. I guess one thing that you might concede with the other one is perhaps there's less code being added with the other one, whereas here you might potentially write more code. But I would still say that that is well worth the effort. I think it was earlier in this class. There's certainly other classes where I talk about it, where you get fluent with some programming, and the tendency is to want to eliminate things all of a sudden, right? You're getting pretty good with kind of breaking apart your logic, and rather than having 10 functions to do this, I'll just have one function and throw a switch statement in there. And then you find yourself doing stuff like this. And so the argument is to get past that, and really it's worth writing more code if, one, I suppose readability is a big one, but also if you're pushing decision making down to the compiler. Because writing the code takes the least amount of time. It's the debugging and the maintenance that take the most, debugging relatively, but certainly maintenance is a huge piece of that. Regarding the polymorphism piece, what's being done here is we have a normal member function. We just throw the word virtual in front of it, and what that's affecting is affecting how that function is invoked when either you're invoking it through a pointer or, as was shown here, through a reference. And when you call a non-virtual function, like set color, there's no virtual here, the decision as to which function is going to be called is made while the program is compiling. So meaning on line 51 or on line 55, the decision on which function to call is made while the program's compiling. In this case, it would be that function that is part of the shape class. You can go up here and look at it. Where is it? Oh, there it is. By contrast, if the function is virtual, then the decision, which stats is an example of, then the decision as to which function is going to be called is not made until the program is actually running. Okay, so that's the distinction between them. And the idea is simply that we have interfaces. I would call this an interface. What the function returns, the name of the function and its input parameters. The interface is the same for all the classes, but its implementation is different for each of them. And that's kind of the pattern you look for in order to shove the word virtual in front of it. So the remaining questions, which start to dig down a little bit, are: one, why do we have to put the word virtual there? I can write functions in, I can have this inheritance relationship and write classes in my derived classes, or excuse me, write functions in my derived classes, and in Python it seems to do the right thing. In Java it seems to do the right thing. There's no keyword virtual there. Why do we have to do it in C++? The short answer is because of C. The longer answer is take 511 next semester. In 511, we actually create a polymorphism engine in the C language. And then you know exactly what C++ is doing under the hood. In fact, you know exactly what it's doing with member functions. These are probably not what you're expecting either. The equal 0. This means that it's a pure virtual function. What that indicates is that the class in which you put the equal 0. Now note it's in the class declaration. There's no definition of a function that has equal 0. So it's just right there where you're creating the class. The moment you take any virtual function, by the way, if it's not virtual and you do that, it won't compile. So the moment you take a virtual function and you throw equal 0 in front of it, seasoned developer is going to say, aha, that's a pure virtual function. They throw the word pure in front of it. And the side effect is you are unable to create an object of that class, in this case shape. What I mean is if I write a line of code that looks like this, or a line of code that looks like this. Let me see, do we have a constructor? Neither of these lines will compile, and it'll say words to the effect of what I've said. It's an abstract base class. You can't create objects of that type. Okay. So what about classes you derive? Classes you derive. So here, I guess I should talk a little bit about inheritance for those who are hazy on it, but let me come back to that discussion that I should have done a little bit earlier. This class is derived from it. I will be unable to create circle objects where is it? If I do not write a version of the stats function in this case. So shape class is pure virtual, or shape class is an abstract. It's called an abstract base class, abstracting that you can't create objects of that type because it has a pure virtual function. You feel free to derive whatever class you want off of shape, but if you derive a class off of it, that one's going to be abstract and you can't do anything with it. You can't create an object with it unless you write your own version of that pure virtual function, meaning give it a definition as was done, well, right here. And so that's an interesting way for a designer of a class. Maybe you're going to design a class that is intended for other people to derive off of. A good example, actually, would be the OStream, right? We're all familiar with OStream and OFstream. OFstream is what cout is. You can actually derive your own class off of OStream, but if there are any pure virtual functions in there, you're going to have to write your own version of that function if you want to create an object of that type. It's that kind of thing. It gives the class designer some power over how you derive off of it. Now, regarding the mechanics of inheritance, this, of course, is a syntax, just merely to say that a shape is a kind of circle. When I create a circle, what data is inside of it? So if I was to come over to my diagram here, let's ignore that for a moment. And I was to create a box called circle. And then I had to say that circle had some data to it. What is the data inside of circle? Radius, yeah, it's right. You can see it right there, right? I don't think there's any controversy there. Anything else? Color from shape. Absolutely. In fact, if I wanted to be somewhat more accurate, I'd put it first. So inheritance means that this derived class is inheriting not only the functionality, but the data as well. And if you look at the bits and bytes, I'm not just doing this for the semantic conceptual understanding. Literally, if you were to crack open a debugger and examine a circle, you would see color and you would see radius. Those two variables comprise every circle. So even though they're separated here, that's for our benefit as programmers to create these abstractions and to pursue object-oriented designs. The actual implementation, a circle is all of the data in circle, and it is all of the data in the base class, or base classes, right? The hierarchy could go for some time. And it accumulates all that data further up the hierarchy, and that's actually sitting in those objects that you create. All right, so any questions on that? Okay. I have to sneak a peek here. All right, so in 111, I give a little bit of a talk about how expressions are evaluated. And I would say something like what the language is doing is it's taking, say int a equals, it's basically taking this starting point and then it's evaluating this and it's returning the result. So I guess what I had to do is this. And then it's evaluating that. So that becomes 24. And then it's evaluating that. And then, actually, let me get rid of the declaration part. Okay, that's actually what's happening. And in fact, lines 5 and 6 are perfectly legal lines of code that you can go ahead and compile in a program. I'll be the first to say that they're not very useful. And in fact, compilers, they didn't used to, but compilers nowadays will usually give you a warning saying, hey, this is kind of useless, are you all right? But it is legal in the language, and for the reason of what's being shown here. What happens with these expressions is they're actually, there's a tree that's actually built, and a tree in the traditional sense that you learned in data structures. And it would look something like this. And what happens is when it comes time to evaluate this expression, there's a call, there's the top of the tree, and at the top someone tells plus evaluate, and the first thing plus does is the plus has let me see, I drew this as kind of an inheritance and I shouldn't have. You should all be going the other way. All right, so plus turns to the left-hand side. So there are two pointers that plus has. And plus turns to the left-hand pointer and says evaluate. And now this thing's been asked to evaluate, and it turns to its left-hand side and says evaluate. This turns to its left-hand side and says evaluate. And this is a constant number. And so when it's asked to evaluate, it just gives itself back. So now this thing has a 3 sitting up here. Let me see. Maybe I'll choose an exciting color. Yeah. You want to party with me when I say that's an exciting color. Come on, I got some letters and a can of paint. Come on over. All right. So That's asked to evaluate, it comes back with 3. This is asked to evaluate, it comes back with 4. And now that this object has asked both sides to evaluate, what does it do? Say it again.
It evaluates.
Let me see you after class. All right. What does that mean, though? Yeah. It does the algebra. Yeah, the arithmetic. And so let's back it up. This asks its left-hand side to evaluate. What does it get back? Yeah, exactly. Oops. And then it asks this side to evaluate, and it just returns itself, which is 2. And again, same idea. This object asks the left-hand side to evaluate, and what it gets back is 24. And of course, I'm sure there's absolutely zero mystery going on here. It's going to be 1. And then all right, so one of the key insights, now this isn't supposed to be hard to understand, and I'm sure you have this well in hand, but here's the key insight. The tree is set up and it just sits there. And the evaluation doesn't happen until the top of the tree is asked to evaluate. Then it'll look down and ask each of its to evaluate, right? And then the chain begins, and a constants come up, and once these are all binary operators, obviously. Once one of these binary operators has asked the left-hand side to evaluate, it's guaranteed to get a constant back. It asks the right-hand side to evaluate. It's guaranteed to get a constant back, right? It doesn't matter whether it's at the bottom of the tree here and you ask a 3 to evaluate and it's already constant. When you ask a constant to evaluate, all it means is that it returns itself. But what's wonderful about it is not only do you have the obviousness of down here in the tree, but up here, this really doesn't have any concept of of what is on the left-hand side. It just blindly asks it to evaluate, and magic happens. You can be assured that a constant object is going to come back. Same on this side. Once it has 2 constants, you can do your operation on the constants, in this case multiplying them together, create a new constant from that, and give that new constant you just created to the person who asked for the evaluate. So this is where polymorphism comes in. If you look at each of these as objects of a class, you could call all of these integer constants. There could be a class called integer constant, and there is. There is a class called, I don't know, multiply, a class called plus. Every one of them has a function called evaluate. Doesn't take any input parameters, but it will return a constant object or a pointer to a constant object. Okay? And so that's where we're getting the polymorphism. Now this is more what it actually what that class hierarchy looks like. We create an expression class. It has a function called evaluate. Do you think we ever create objects of this type? Do I ever say expression e semicolon? No. So what do you think is true? What kind of class would you call it? an abstract, in this case, a base class, an abstract base class, right? And it's abstract because at least one of its functions is pure virtual. Which function do you think is pure virtual? Evaluate, which means if you ever want to create an object further down, like if I ever want to create an object of this type, I have to write an evaluate function for it. Same with these. What about here? There are no objects of this type created. Why do you think this is broken out? So I would say this is abstract. I would say these two are abstract as well. Why did I break these out?
Different number of variables. One comes only on the left-hand side, the other is left and the right-hand side.
Right. So looking at this tree, these are all binary operators. If I had a unary operator, like taking the negative of something or taking the sign of something, then it would only have one branch coming off it. And what that looks like, right, we can say A equals sine 3 times 4 plus 5, so that this, or in fact, let me just borrow straight from this example here. Then I would have, let me see, I'm at the top of my, let me use this cool one that, let's get out of here. Oh, I guess it's showing me all my opportunities. Okay. Here it comes. There, all right. Now let me stop that. Please let go of me. Thank you for playing. All right. So this is sine, right? Unlike these binary operators that have 2 pointers coming off them, this one only has 1 pointer coming off it, which is to this whole tree, which is a realization of that expression. So using this hierarchy, we can create any legal expression in the language. And again, the key is that you build the tree because what you're trying to push out is the point in time where you evaluate. And that makes sense if you think of C and C++, because what if I do this? Let me say A plus 1. All right. What prints out? So 8 is a global variable. What prints out? Right, no, it's not a trick question, right? You don't have to be scared about answering. Yes, 11. 11 prints out. So why don't we, when we're compiling this, why don't we just evaluate it right here and just change the, let's just evaluate it right away. Forget the tree. Let's just evaluate it. There we go. 11. Yeah. The compile. What if you say if user entered a vowel, set A equal to 50, right? And obviously this is something you can't know until the program's running. So that is why you build these trees and you don't evaluate until this function is called and you're actually running this statement. Then you evaluate. All right. Let's look at a little bit of code. Let me see. How do I want to do this? Yeah, we're definitely going to be going well into Thursday on this. A little bit of code. So if I look third project, and there's a p3.tar. I've got that here. Note that this is my bin directory that has those utilities, and in source I've got I have P1 and P2. I've got other crap in there as well that you can avert your eyes and ignore. So make sure you've got P3 wherever P3 is. Make sure that your current directory is shared with bin and source, and then that'll in the source directory it'll create P3. So now I go down to P3, or excuse me, I go down into source, and then I copy P2, basically everything from, let me not do that yet. Let me go into P2, let me make clean, get out all the cruft, do an ls, I've got a little test code there I can get rid of. What else is there? I probably don't need the README stuff, but I guess I've got a couple other extra bits of trash from playing around in there. But what I can do is I can say copy from P2. I want all of the CPP files. Let me do this the other way. Let me start from P2. I want to copy all the CPP files, the H files, the .L file, the .Y file, the make file. Am I missing anything? I think that's probably everything. And I want to copy that into P3. All right, so there's my starting point for P3. One thing about P3 is I do not yet have completed a nice write-up like I did for the other ones. That's coming, right? That HTML, I don't know why I'm going to show it to you. You've probably been staring at those things for hours on end. The numbered list of things to do. I don't have that written yet. I promise I will get that done. In the meantime, there's this expression grammar.txt. It's also part of the tarball, so you can find it in your P3 directory. This is just a real quick bit of information on what needs to be done. Now, don't panic. There's a lot I haven't talked about what needs to be done. In fact, I'm going to dedicate Thursday to kicking off this whole thing. Okay, so I will be providing a lot of information that I think is going to make it pretty clear on what you need to do for this project. But before we get there, let's look at the source that was included with that bundle. First is I have provided where's my drawing? Let me choose this color. Well, so much for putting a nice box around this. Why is that doing that? Stop that. No fill. Did you see that? Right under my nose, too. It's not even trying to be... I'm going to have to... Let me see. Well, if I just simply... Alright. I'm learning. Let me choose this color. Let me do this. I'll use this one. Let me do that, do that. All right. This whole thing is constant dot CPPH. Okay, I guess this one will work. So that's what these files are, minus this variable one. Let's pull. And then all of this stuff is going to be in expression.cpp&h. So I guess I need to move that there, maybe like that. And then I take this box and let them match. So something like that. All right, so let's look a little bit. The constant class hierarchy has been completely provided to you. This is what is these bottom bits of the expression tree, these constants here. Okay. Note they have an evaluate function. It's because it's inherited from expression. I guess it's worth looking at the expression for itself. There's more here than we really need to worry about right now. It's got a constructor. Don't worry about that. I just want to focus on this one function. So there it is. The expression class has a pure virtual function called evaluate, and it returns a pointer to a constant object. That means any object that is derived from the constant class. And you'll note that integer constant, double constant, and string constant are all derived from the constant class. Constant itself is derived from expression, so if I want to create any constant object, I do have to write an evaluate function. And that evaluate function is written right here. Now, interestingly enough, I did not write an evaluate function for the classes derived from constant, and there's a very good reason for that. Let me look at constant.cpp. Let me just grab that code and paste it here so we can see it all together. Doesn't matter what kind of constant object it is. We look at this diagram. Doesn't matter whether that's a float or a double, an integer, or a string. It's just going to return itself because it's already a constant. Then there are three functions that need to be supported by these classes. And that is a request to please give me yourself as an integer, please give me yourself as a double, please give me yourself as a string. And the integer constant, if I'm asked to give myself as an integer, you just return itself data, right? Note that integer constant has an integer as data, a double is data, and then of course a string is data. If an integer is asked to return itself as an integer or as a double, it just returns itself. No problem there. If it's asked to return itself as a string, then all you do is you just run through this conversion function in the standard library to convert a number to a string, and it'll return itself as 1 or 2 or 3 characters, depending on how large the number is. Double, now it gets a little bit interesting. Returning a double is fine, or returning a double as a string is fine. Again, you call this simple conversion function. However, you cannot, in GPL, that will not compile. That'll generate an error. And the way we normally think of functions is if the function works correctly, you return some value, and if the function has a problem, you return some sort of error code. Well, the problem is, what possible error these functions? What do I want to look at? This function is supposed to return an integer. What possible integer could I return to indicate that it's unable to do the conversion, that I have a problem? And the answer is none, right? If it's 0, then the double must have been 0.0. So we need a totally different mechanism for error reporting, and that is where exception handling comes in. I won't talk about it right now. We'll talk about it a fair amount on Thursday when we start implementing some of this stuff. But suffice to say, if there's a problem, you just throw an exception. If everything's fine, you return that value. And then string, it's nonsensical to create a string s equals 32 or 33.2. So each of those should be throwing an exception, and then the only valid one is to ask a string as a string. Okay. So that's a sneak peek at the code we're starting with. On this side, oops. So the base expression class is provided, and then I've provided the binary operator here. I've not provided unary. I'm going to leave that to you to write. But I provided a binary operator and kind of the shell for a couple binary operations to add and to multiply. And so what I want to do on Thursday then is show how we can go into gpl.y and start implementing this project. Okay? So I'll go ahead and end it here, and we will just pick it up with actually implementing it. And you'll be surprised, it'll actually all come together very, very nicely once you start seeing these put into gpl.y. Okay? All right.